2, 3. And we talked about these different ways to evaluate limits. So we have these limit laws. It's a really good thing to get to know these, okay? So what you want to know are a couple of things from 2, 3. You want to know that when you're dealing with limits of roots, you can bring the limit inside the root. When you're dealing with limits of rational functions, or polynomials, you can do direct evaluation, okay? And we're going to extend that set of rules today by talking about continuity. But the last thing we want to deal with is this thing called the squeeze theorem. So, very often there are functions that don't fall into any of these categories. And the squeeze theorem basically says that if we can bound the function we're looking at by another function, that's going to help us figure out the limit. So this theorem starts off with a kind of fact that's somewhat obvious, maybe. It says that if you have two functions, f and g, and they're going to be defined on some interval. So I'm going to be interested in the limit as x approaches a. So I'm interested in the limit as x approaches a. And in this little interval, there's some little interval containing a. I might not be interested in a itself, but in that interval, the function f that I'm interested in is bounded above by another function g. Okay? In that entire interval. And if that limit of both of them exists, okay, so notice I have to know a lot of things. I have to know that the limit exists, and I have to know that g bounds f. Then we're guaranteed that the limit of f has to lie below the limit of g, the top function. And that makes sense because if the limit didn't, it would have to be at some point above g, which means the curves would have to cross. That's kind of an intuitive way of looking at it. So this is a very nice theorem because it leads to this result called the squeeze theorem. And the squeeze theorem is sometimes called the sandwich theorem. It's called both, and there's a nice reason why. So here's the situation. Now we have this function g we're interested in. So what I'm interested in is the limit as x approaches a of g. This is what I want. And I know something about what's going on in a little interval around that point A. I know that there are two other functions called h and f. And h bounds g from above. In other words, the graph of g always lies above. The graph of h always lies above g. And g is also bounded below by f. So the graph of f is always below g. And if I know this is true in some little interval, notice it doesn't have to be true everywhere, but there has to be some little interval around A. So something like this. In this little interval right here, you can see this is always true. It's true that h of x, well, we're used to drawing inequalities the other way. Let me do that. F of x is less than or equal to g of x is less than or equal to h of x on this yellow interval. And I don't care what's happening in A. Sometimes we call that little yellow interval the neighborhood of A. It's kind of like its neighborhood. It's where it lives. And we call it, when we take out that point A, we call that the deleted neighborhood. In other words, we don't care about the person, we're just interested in their neighborhood. So if all of this is true, and the limit of these two bounding functions exists, then we know that the limit of g of x is equal to the limit of these two other functions. That's the import of the squeeze theorem. Now, the reason why it's called the sandwich theorem is because those two functions sandwich the function we're interested in, right? Kind of like they're the meat of the sandwich, right? And it's called the squeeze theorem because as I'm going to that point, what happens? Those two other functions, they squeeze the function we're interested in. They jam that function and they force its limit to go to their limit, okay? So it's kind of a cool little theorem. So you hear it called both, but that's why. It squeezes, it sandwiches, and then it squeezes, okay? Now, how do we use this? So here's kind of the tricky part about the squeeze theorem. Notice that you have to find the two functions, and they have to converge to the same limit. That's not given in the theorem. It's saying if you can find these things, then our job about this function in between is easier. So you have to find that. So how do you find that, okay? So let me kind of give you an example, and then we'll talk about some general rules. I'm going to change this, if you don't mind. I'm going to change this to sine of pi over x. So let me change this. I like that weird function. Okay. Now remember what sine pi over x is. Sine pi over x was that weird function that was oscillating a lot. In fact, in MATLAB, let me see if I can run it real quick. Yeah, shoot. I'm sorry? A little bit. Yeah, I'll tell you what. Okay, so I want to make sure everyone got this, but let me just show you this really quick, and we'll go on. Okay, so this is that function. Hold on a second. So this is that function, sine of pi over x. Okay, I just want to show you this real quick, and then we'll move on, because some people didn't seem really good about the squeeze theorem. Okay, so notice that that's that weird function, right? I want to convince you that the limit does not exist at 0. So you can see that limit doesn't exist. The function goes in more and more. Yes, ma'am.
How did you get MATLAB to do that?
It's just a program. If you want, I'll actually post the code. Okay, but here's the key point. Is that, so I want to go back and just kind of talk about how to find these functions really quick. So this function does not convert because it approaches 0. You can see there's no value. What has to happen when a function approaches 0? You have to converge to this value. This function is not converging. So I want to just give you a few really quick rules, and we'll move on. So here's the quick rule. The quick rule is then when you deal with limits, I can get this to work. So there's 2 rules. Now I can't write. Let me try it again. I don't know why it's doing that. Go down a little bit. Here we go. Okay, so here are the rules for the squeeze theorem. 3 rules. The first is that when you have the limit as x approaches 0, and you have x multiplied by any function that's bounded near 0. Okay. Notice that's what's happening with x times sine, right? And by the way, it's not just x, it's any power of x, root of x or any power of x, right? If I have a situation like this limit's always 0 because this thing is bounded and the x is squeezing it, right? Function bounded near 0. So we just write bounded BDD for some reason. Mathematicians write it. So this is the sine function, right? Question? Whenever we have a trig function, the first thing we want to use when we have a trig function. So this is rule number 1. When we have a trig function, sine or cosine, have to be careful. Okay, it doesn't work for tangent. But when you have sine or cosine, we want to use this fact. Okay, and it's also true for cosine of x. And you can put anything inside the argument. It can be pi over x. It can be whatever you want. But we're always going to use that inequality. Okay. I'm sorry? Sine of x and cos of x. So for any of those functions that are bounded, we're gonna try to start with this inequality and get the squeeze there. Okay. So I just wanted to go through that quickly because that was kind of something that I know people were a little confused on. Okay. So let me print out the next set of notes. So we were talking about yesterday functions that were continuous. So I just want to review something real quick about that. Yes, this is what I want. So the thing that I want to emphasize here So the whole point of this handout is really twofold. First, we want to realize that the point of continuity is that it helps us evaluate limits. You want a continuous function because the limit is trivial. You just put in the value that you're converging to. So continuity is a really nice thing. Now, the thing is, you have to make sure the only thing that you need. This is not what I want. It's the other handout about the. This is the one that we're going to. Let me download the other one really quick here. Well, I tell you what, that's okay. I'll just write it. I'll just open up a page. So here's what I want to say about the section where we're talking about continuous functions. The whole purpose of continuity is that it lets us evaluate limits. We don't have to go through all this baloney of all these rules. Can I move something inside the square root or whatever? So the whole point is that if f of x is continuous at a, then we evaluate the limit by direct substitution. So in other words, the limit as x goes to a of f of x is equal to a. So that's the first take-home point. The other take-home point is that almost every major function that you know is continuous in its domain. So this makes life easy because all of those functions you know from pre-calc are continuous in their domain. There are no exceptions. So I'm going to say all with the caveat that you understand by all, I mean all the functions that you've been exposed to, okay? CONT is just continuous. And that's why I'm going to go back and emphasize it's absolutely imperative that you go back and look at those functions and make sure you know what the domain. In other words, what are all the x values you can put in the function and not do anything mathematically or evil, 5 by 0 or 4 or something like that. Okay? That's what we need. The last thing has to do with, how do you get the domain when you have compositions of functions, when you have combinations of functions? And so the idea is, so when you have a more complicated function, you don't have a single function, but you have a combination. Yes, sir? All functions are continuous, CONT. Continuous in the domain. All right, the last thing is that when you have combinations of functions, the last thing, the first thing you have to look for is values that, if you have a ratio, values that make the denominator what? 0. So that's the first thing. You're not going to be continuous there. So I have to look for x that make denominator 0. Oops. Denominator is equal to 0. And basically, the rest of it is, I'm going to look at the intersection of all the domains of the other function. Because every single one of them has to be continuous in order to use that law. That's the idea. You have 4 functions, you have to figure out the domains of all those 4 functions and take the intersection. In other words, what points do they have in common, right? And that's where they're all guaranteed. And that's only the last take-home point is that we want to take the intersection of the domains of all the functions. And usually and actually there's a little bit of a sub-strategy here, which is we would like to use the functions that have the smallest domains, right? So I see like natural log, I like that. Because what part of the x-axis is natural log? And 0. So I know automatically that I don't have to even think about those. Then I can focus on the rest. The ones that are hard are the ones like tangent, where how many points is tangent discontinuous at? Minus pi over 2 and pi over 2. Are those the only two? Periodic. Every 2 pi. So that's the hard one. So how do you represent that? So let's just kind of look at this really quickly. So, for example, suppose you want to ask, so the trig functions are tricky. So if you want to look at where, for example, tangent is continuous, well, we know that it's discontinuous at minus pi over 2 and pi over 2. But we know that every time we add 2 pi, it's discontinuous at those points too, because trig is periodic. That it's a periodic function. So how do we represent that? What we say is all odd multiples of pi over 2. Okay? So this is discontinuous at all odd multiples of pi over 2. Or if you want to be mathy about it, you can write it as 2n plus 1 over 2 times pi. Same thing. So if you want to write that out, you could say, like, for example, suppose I had a natural log and I had tangent added. I would say it's all positive x except odd multiples of pi over 2. And I wouldn't even try to write it out in any sort of notation. I'd say in words. But it's just way too difficult to try to write out. Okay. And that's the problem that we ran into yesterday. So that's why I wanted to go through this quickly. Okay, any questions about this? Make sure everyone's up to speed. So let's go back to our regular scheduled program. Let me just make sure, did we get through, I just want to make sure we got through everything on that handout really quick. Let me just look. Come on, open up. Gotta take a while to open up. I apologize for the technical difficulties, but I do want to make sure that everyone gets this. Okay. So let's just make sure we got through all of this. I think we did. Yeah, okay, good. Okay, so now we're actually kind of back to where we ended. What do we do when we have algebraic combinations? Okay? So here's kind of the cool theorem now. We can kind of make things a little more simple by saying that now if we have functions that are continuous at a point, and we want to look at algebraic combinations. So we want to look at addition, sum, product, multiplying, and numbering. All of them are continuous. This actually, if you think about this for a second, this is a generalization in a sense of the limit laws we had way back in 2.2. We said if two limits exist, right, or sum exists, it's kind of a generalization. It says that if they're continuous, algebraic combinations are continuous, with the big caveat that you have to watch out when you read the numbers here. And that's the point that's going to make things break down. That's the point you have to really watch out. So this is the case where things get kind of hairy. Okay. So we started on this yesterday, and we said, okay, this is the limit as x goes to pi of 2 plus cosine x over sine of x. Okay, first of all, so what we want to do is we want to look at this. We say ratio. It's not a polynomial. kind of our thought process, right? So we look at this and we say, we got a ratio, not a polynomial. It's not a rational function. Because if we had a rational function, we would use different strategies, right? Necessarily. So the first thing we're going to think is, do we have continuous functions for every term in that expression? Okay? So in other words, I look at every single thing here, and I want to know, is every function here continuous? At pi. The answer is yes. Okay? So the next thing I ask is, are all my functions continuous? Good. Is it okay if I just say CONT for continuous? Everyone's cool with that? Okay. And the answer is yes. Okay, so what's the last thing I have to ask? There's one last question. I'm almost there. I got a ratio, they're continuous. Does that denominator 0 have that? We have to kill it. Does it? So what are we worried about? We're worried about the denominator is 0. So what are the values that cosine take on? You go between -1 and +1. So the very smallest this can get is when cosine is -1, and we're going to be out of the way. Very good. Piece of cake, right? So we're going to be okay. So then we can just use this theorem. This theorem says that we have a ratio, everything's continuous, the denominator does not go to 0, so what do I do? Throw pi in. Just substitute. So does the denominator go to 0 as x goes to pi? No. So I just substitute x equal to pi. And that's it. And we're done. So what is our answer? Let's go ahead and do it. Answer is equal to sine of pi over 2 plus cos of pi. Well, sine of pi is 0, so I don't even care about the bottom. Okay, it ends up being 0 over 1, which is 0. And that's it. Notice how nice this is. No pictures, no laws, all we use is and that's how we're going to approach this. Okie doke. So we dealt with continuity at a point. It's really important to make the distinction between continuity at a point and continuity in a region. A region's talking about an interval, right? So this problem is talking about continuity at a point. Okay, this problem is using continuity at a point. In other words, I want to know what is the limit, and I'm using a property of continuous functions. I want to know what is the limit at a specific point, and I'm using properties of continuous functions to get at that. Okay? So that's one use for continuity, evaluating limits. There's another use for continuity that I'll just mention really quickly. You have to be continuous to have a derivative. We're going to see that later on. That's what we call a necessary condition. So continuity is useful there too. All right, but now we're talking about continuity in a region. So this is kind of what we were dealing with yesterday. This functions like this. So I look at this. What is the form of this? What is the form? The first question. Root, sum, ratio. I have a ratio. Same sort of questions, right? Not a polynomial. Do I have continuous functions? Yes, all of these functions are continuous on their domain. So this is a ratio of continuous functions. Okay. But when I want to get the region, what am I going to have to do? I mean, I'm going to have to look at the intersection where all these things are continuous, right? So I start off with the arctan. What is the domain of arctan? So this is what I have to do. I have to figure out the domain of each function, right? So the domain of arctan. I'm just going to write, this is how we write domain. Theorem. What is the domain of arctan? What values can arctangent take in? Someone try to say it. Give me the rest. Yes, sir. Hold on. So, you can write this different ways. You can write this like this, or all x, or you can write the fancy mathematical symbol for all the real numbers. How did he know that? Suppose on an exam you get stuck. How do you know what the domain of arctangent is? It's the range of tangent, right? They're inverse functions. That's what arctan. That's why I wrote the -1. So what is the range of tangent? Well, think about tangent. It goes from -infinity all the way up to positive infinity. The range of tangent is all the real numbers. So the domain of the arctangent is going to be all those numbers. Okay? What about the domain of natural log? All positive. So we like natural log. Natural log's an eliminator. It takes a lot of things out, makes life easy. Whoops. And you can write this as 0 to infinity, or x greater than 0, or all positive x. I don't really care. It doesn't matter. Okay? As long as you know. What now? The domain of x squared minus 1 is everywhere. It's a polynomial, right? What do I have to watch? In this case, right? So I have to watch where the function is continuous and where it's 0, right? So here, and I'm going to be a little careful. I'm not going to write domain because it's not the domain. The domain's everywhere. But the values where this is non-zero. So this is the values where x squared minus 1 is continuous and non-zero. This is going to be, and you can write this various ways. Basically, the only values that are excluded are plus or minus 1, okay? So I'm going to write this in a mathy way, but you can write it however you want. Basically, it's saying it's minus infinity to -1, and -1 to 1, and 1 to infinity. But I've used an open interval, right? So I'm not including the interval. And what do I want to do? It's a mess, all this information. What am I going to do? What's the domain of all of them together? It's the natural intersection. And so this guy is nice. Natural log weeds out a lot of people. Okay? So notice something right off the bat. Arctan's a non-issue, right? Because it's happy everywhere. So we don't have to even consider arctan, okay? It's already continuous everywhere. It's not eliminating. We're looking at the functions that are eliminating values of x. So I'm not even going to worry about arctangent here. Okay? Just put a line through them. So these are the values. So if we draw this, natural log's continuous here. And then if I look on the if I look on the rest of that interval, if I now look at this function and I ask where in the positive values of x is it continuous, it's everywhere except positive 1. Okay? So now I take the intersection, what do I get? Well, I get 2 intervals, right? Everywhere from 0, but not including 0 is included. Everywhere up to 1, but not including 1 is included. And then all these values after that. Fine. So now I'm going to take the intersection. Okay, I'm going to use a little symbol for intersection. And what I'm going to get is this. This is 0, and this is 1. If I want to write that, the answer is going to be 0 to 1 union 1 to positive infinity. Or, if I wanted to say that in words, how would I say it in words? just all of the positive fields, right, except one. So there's a method for that. Right? And like so. Okay, questions on that? Sure. Questions about this? And I will actually post it. I'll post it on that. Along with it. So someone want to say? So you got it. Go ahead and say it. What? Good. Any other questions? This is an important example because this is the sort of thing you see definitely on the exam. There's no doubt about that. Okay. Compositions. So this is a little tricky because we don't deal with compositions a lot, but compositions become increasingly important in calculus. What is a composition of a function? They get together in the jam, or what's a composition of a function? But I don't know, what is a composition of a function? I don't know the composition.
What is it? Multiple pieces of function?
In a sense, but I'm looking at it a little more direct. Put together how? I can multiply. You can redeem yourself. Function of a function. You can see why we don't deal with them a lot because they're complicated. One function inside. Right. So the argument. So we have a thing called an outer function and an inner function, right? So this is what we mean by this. Okay. I don't like this little dot. The book uses the dot. I don't like it because I think it kind of hides what's going on. So I'm going to write compositions like this. So notice that g of x is what we call the inner function. We sometimes give these names. This is the outer function. This is the inner function. So, and it's complicated for a lot of reasons. A, we don't do it, and B, the notion of function is something that really kind of takes a little while to get your mind around, to be honest. So let me just kind of give you an example. Suppose f of x is equal to x squared and g of x is equal to x plus 1. Then what is f of g of x? Which the book would write like this. The book writes it like this. Which I'm not going to write it like this. What is this? Go ahead. F of x is x squared, so whatever's inside of this gets squared. Well, what's inside of it? What's inside of another function? X plus 1. Right? It just becomes x plus 1 squared. So that's the idea. This is the inner function, x plus 1. This is... and I could actually write this. If I want to be a little more careful, let me rewrite this, just being a little more careful like this, just to be a little more thorough. I'm going to write it like this. I'm going to write it as g of x squared. This is what f of g of x is, right? And what is g of x? X plus 1 squared. So, wrap our mind around that. Now we want to look at when are these compositions continuous? This happens a lot. A lot of these things. So this is a theorem. It's a very weak theorem. It's useful. What it says is this. It says that if you're looking at an inner function and the limit exists as x approaches a, so let's kind of look at what we're trying to do here. So we want to look at the limit as x approaches a of f of g of x. This is what we want. And the theory, yes, sir. Oh, I told you up here. Yeah. I just want to kind of give an example to make sure everyone's cool on knowing how to evaluate the composition. This is something from your pre-calc that we have to kind of have it. Yeah. Okay. So what I want is I want this function. So here's what I need. I need G to be continuous at A, and I need F to be continuous at G of A. All right. This is what I need. This theorem is kind of weak. This theorem says you don't have to be continuous. It says as long as the limit of G exists as I approach A. But we're rarely going to have that situation. So what I need is I need to know that G is continuous at A. Or if you want to use the weak version, but what you're not going to use is just that the limit as G approaches A exists. We're not going to use it that much, but technically you can relax this condition. G of X exists. Okay? And the second thing I need is I need F to be continuous at G of A. Exactly, and that's what makes it complicated, because the function on the outside will really interested in what's happening to it at G of A. It takes a little while to If we have these two conditions in evaluating the limits, we just substitute. Continuous functions, what we say is compositions of continuous functions are continuous. So that's beautiful, because now if we have all this, it follows that the limit as x approaches A of f of G of x is equal to f of G of A. Continuity is what we like, because limits at points always direct to value. Because what this really says is that given these two conditions, the composition is continuous. So we think of f of G of x as a new function, like h of x. Okay? So this is because f of G of x is continuous at A. Okay? And this is the picture that I've drawn to try to illustrate this, okay? So this is the weak version of the theorem. Notice that as x approaches A, I'm going to put A in there so you know what that is. 1, 2, 3, 4. We'll just say 4 here. So in this case, you want to notice that, use a different color, that the limit as x approaches 4 of G of x is equal to what? Looks like 2, right? Notice that G is not continuous at 2. This is the weak version of this theorem. We're not going to use it a lot. Listen. Good question. So let's see the theorem. So this theorem says that this value approaches, this limit approaches a value. Now we look and see what happens as G of x approaches 2 for f of x. So now 2 is going to be the argument of f of x. It is f of G of x. So this value is now the argument of f. So what happens as G of x approaches 2, this approaches 2. And it's hard. We don't really have a notation for G of x approaching 2. We're used to x approaching values. Makes it a little tricky. So the idea is that this approaches 2, but here the argument of f is really G of x. So we look here and say, what is the limit as the argument of f approaches 2? Let's say it that way, okay? So the limit as the argument of f approaches 2 of f of whatever's inside of here, okay? Here it happens to be a function. And we can see that that's equal to 1, 2, 3. So that's our answer. yeah, the function here as x is equal to 2, as x is equal to 4, g of x is equal to 2, right? So like the argument of f, which is how g of x is equal to 2, this goes to 1, 2, 3. Does that make sense? I'm not sure. Okay, what's So here's the thing. So we're going to look at the limit of f of g of x. So first we say what's happening to the inside function as x approaches 2. That's, I'm sorry, as x approaches 4. Right? Be careful. Right, because we're looking at, so let's kind of go back and think about the problem we're looking at. We're looking at the limit of f of g of x, right? As x approaches 4. Okay? So first, so what we're doing is we're evaluating. So this is the problem. This is the problem we're doing. So this is the idea. As x approaches 4, the inside function approaches 2. But the argument of f is the inside function. Okay. That's the idea. And if g was continuous, it's trivial. If both of these graphs were connected, we just plug in whatever. We wouldn't even deal with it. We would just say f of g of 2. Just the value of the inner function or the outer function. Exactly. Yeah, just substitute. So continuity means substitute. That's how I think. Continuity, evaluate elements, substitute. Okay, we got a few minutes. So time for the name game. Let's do this. Oh, by the way, I want everyone to. But does someone have my roll? I didn't get my roll back. Someone said they had it yesterday. I did not get it back. Grrr. Someone took my roll. So I'm going to need everyone just to check off their name for today, okay, please? Let's put this someplace where we won't have a huge scandal. Okay. I'm sorry? Yeah, just go to the date and. Okay, so hold on. Name game. Who wanted to go? Okay, I don't know. Go ahead. Carla, I knew I had you before. Okay. Oh, not a big one.
Yeah.
Some people look different. Some people look different.
So is that 2? So I get 2?
You get 2 extra credit points, but you will not get a third. Zach.
I will get 3.
There's Zach. Okay. Josh. I got 2 out of 3. I'm getting better. Okay. Be safe, guys. I'll keep you updated as soon as I know stuff about the hurricane. I promise. Okay, but don't worry. It'll be fine. What's up?
I do. Can I start on the
Yeah. If you can work ahead, that's perfect.